indications, and that will mean that 3 LEDs will be lit for a ½ watt, and if you see 4, we've hit 1 watt. So we'll put the camera in the tripod. You'll hear a little rattling from this stiff oak tag material until we get it approximated. Let's take the power up now to about 1 watt. There's our 1 watt, and there's our orthosonic lift by radial deflection. You'll see that it's quite mobile. Even the springiness of the wires is enough to move it, and I'll bring the power down slowly. That's about 0.7, 0.6, coming close to 0.5, and it lets go at 0.5. Let's bring it back up, and there we are at 0.6, holding rather well. If I pull it, there seems to be a decent amount of reserve capacity. Taking a view from above, you can see that this is quite mobile. The springiness of the wires provides enough to oscillate the entire system. Quite different than if a magnet were providing the suspension to a metal surface. And replacing the camera, when I power down from our 0.6 watts, it drops. Now, we've used the unported wing, which has the dual purpose of both lifting surface and acting as the diaphragm of the audio driver. And that's an important change because with a planar distribution of sound intensity, the sound intensity falls off with radial distance from the center of the driver. And because this is an unported wing design, we do not sacrifice the area of highest sonic intensity and therefore highest orthosonic lift. Because of that, irrespective of the small driver size, today we have set a new record for lift efficiency with orthosonic lift by radial deflection. And by that I mean that in lifting 34 grams with 0.6 watts of power, we did far more than we did in previous experiments where we used a Polk low-frequency driver and this ported faceplate to lift this pine wing. This weighed about 104 grams, and we used 40 watts of power to suspend that in a similar way than we did today. So this is a 22 times gain in lift efficiency, and I think an important comment on the unported wing design.